Hey folks, this is Captain Jones here to talk to you about something called assembly language. This is going to make our lives so much easier as programmers. Today, our objectives are to kind of define what that is, what we mean by assembly language, and then to show enough of the LC3 assembly language to you that you can write some short programs in it. And so that's going to involve describing how we encode instructions in the LC3 assembly language, and also how we can use something called pseudo operations or assembler directives to craft our programs. So let's get started. Okay. So I'll start here. We have a flowchart that might be the result of our programming process. We've defined our problem, sort of broken it down into these steps, which at this point pretty clearly look like we can implement them in the parlance of the LC3. And this, in fact, is the program for multiplying two numbers together that happen to be stored in these two memory spaces, 3007 and 3008. So what we have been doing is taking this flowchart and essentially at each step converting these sort of pseudo instructions directly into machine code. And you know what? That's honestly, it's kind of gross. But more scientifically, it's really tedious, one, and it's very error prone. It's very much not clear looking at these ones and zeros whether there's a mistake in this machine code in terms of implementing this flowchart. To check this machine code, I'd have to go through every opcode, make sure the opcodes are correct, make sure the branch targets are correct, make sure everything's stored in memory in the correct spot, make sure the correct registers are in the correct fields. And that makes for some very difficult programming. So one level up in terms of abstraction from the machine code is something called assembly, where we don't write code in zeros and ones. We instead sort of we use text and we assign specific mnemonics to each instruction that sort of encode what we want our machine to do. And you can already tell this is much easier to read, even though you don't know quite what this says here. This is much easier to read than the ones and zeros up here. And once you do know what it says, it's much easier to check that this piece of assembly is correctly implementing this flowchart. So overall, assembly is human readable, number one. And number two, it supports these things called labels. So, instead of referring to values that I want to reference by memory location, instead of referencing places that I want to jump in my code by their exact location in memory, I can use placeholders. You notice here, we'll discuss kind of what this is doing in a second, but you might be able to intuit already that if I'm branching to loop, then what I'm trying to tell the computer to do is formulate a branch instruction that will send you back to this instruction here marked by the label loop. And in that way, I don't need to know the exact memory address of this instruction. I can instead put a label here and let somebody else worry about it. I can do the same thing with my values here. We'll talk about what .fill means in a second, but you can see already I'm loading a value into R1, a value into R2, and I don't even know exactly where they are in memory. I just need to be able to I can reference them by name. It is the job of a program called the assembler, which will read this file, and it's its job to convert all these sort of symbols, these labels, into their actual memory addresses and to generate the correct machine code. But we don't have to write the assembler. Someone else has done it, and even if we had to write it, we'd only need to write it once, and then from then on we could write assembly language programs instead of having to write machine language programs. So let's do a quick tour of what's here, and then we'll talk about how we go about converting a flowchart into this. So you can tell this main block here in the middle. In fact, all the words are kind of highlighted here in blue. These are all my instructions. And these have basically a one-to-one correlation, assembly language instruction to LC3 machine level instruction, which means, this LD here, this load, this refers to a specific instruction in the LC3 ISA. And so when I'm writing this in assembly, each instruction line has four elements, two of which are optional. So I can put an optional label at the front to mark an instruction as the possible result of a branch target. I have to provide the opcode that tells the assembler what instruction I'm trying to perform. And I also have to provide as many operands as are required by that opcode. Sometimes the operands are 0. You can see here the halt instruction doesn't require any operands. but for every other instruction, if there's an operand required, I have to provide it. And then lastly, if I want, I can provide some sort of textual comment. That's another optional one. So we don't see any here, but if we pull up the textbook, then you can see an example of a comment here in this piece of code. In the assembler for the LC3 treats semicolons as the indicator that anything else following that on the rest of that line is to be ignored by the assembler. It's a message to the programmer and will not be incorporated into the machine code at all. So that's very useful. You can see here for just kind of annotating what's going on in the code. Yeah, so the operands, I've already mentioned, the exact number varies by the instruction. We're already familiar with a couple of them. For instance, the add instruction, of course, takes 3 operands, the destination register, or source register, and then either a second source register or a literal number. If there are more than one operand, then they're comma separated, or separated by commas. So you can see here I've got comma space, or sometimes no space between these operands to separate them. If we're going to use literal numbers, then we need to identify what format those literal numbers are in by a prefix. Well, LC3 assembly languages uses the pound sign to denote decimal numbers, the lowercase x to denote hexadecimal numbers, and the lowercase b to denote binary. It can also be that if you leave off the pound sign, then the default is to assume that the value is in decimal. But you can see here I've got 2 decimal numbers that I'm working with. Up here I've got a hexadecimal number that I'm using. And the operands can also be labeled. So just like we pointed out before, I can branch to a label. I can load a register from a label, which is specifying some type of value. Here in this piece of code, you've also got a couple of interesting words that start with a period. These are called assembler directives, aka pseudo-ops or pseudo-operations. And so they're called pseudo-ops because they're not actually instructions, but they are notes to the assembler about how to perform certain parts of its job. So in the LC3 assembly, there are five assembler directives that are supported. .org is short for .origin. This is telling the assembler to start placing this code at this location in memory. So that places this function at a specific spot. Every program will start with the .org, and they will complete with the .end. .end is always the one that goes at the very bottom. Once the assembler reaches .end, it doesn't read anything else in the file. So .org and .end sort of start and end our file. And then I've got 3 more directives here in the middle that allow me to sort of create various types of variables. .fill tells the assembler to reserve a single word in memory and given the name on the left, and to place in that location in memory at the start of the program whatever value is on the right. So val1 .fill 5 means when the program starts, val1 will refer to a place in memory and it will have the value 5. val2 .fill 4 means val2 will be given a specific place in memory, and at the start of the program that value will be 4. .blkw, short for block words. What we're doing here is telling the assembler to reserve a block of words, so a sequential number of spaces in memory for use at some point in the future. We don't specify what goes in that spot in memory. The value here indicates how many blocks or how many words are reserved, and then the label on the left just refers to the very first block in that set. So this directive here, numbers.blockword10, will carve out 10 consecutive words in memory somewhere. Numbers is going to be the address of the very first one. We won't know exactly what's in that set of 10 words at the start of the program. This is useful for if you have a variable that's going to be set by a user or set at some point during the computation of your program, but you don't necessarily know the value at the start. You can use block word to sort of just reserve an area in memory for that, and then use it later on. And then lastly, we have a directive called .string_z, which is used to encode, like you can see here, a message of some kind, a string of some kind. And so the assembler will place this message in memory. Message then will point to the very start of this message. We'll look at a little bit later how this actually is put in memory, what we can do with strings. Okay, so let's talk about how we actually convert flowcharts to assembly. Course step number 1, start with .org x3000 at the top, and then for every instruction in your flowchart, you're going to find the opcode that you need. So here R1 gets some memory value. That's clearly a load of some kind. So we're going to write down the load opcode to start. You're going to enter after that any operands that instruction requires. So load requires a destination register. We're going to put R1. We can refer to the registers R0 to R7 just as they are here. So we'll put R1, comma for the next opcode. And in this case, we want to load from a specific location, but I don't necessarily want to put that location. I don't necessarily want to manage that location by its exact value, so I'm going to add a label. So as I'm writing load R1, comma, I'll come up with a label. It made sense for me to make this val underscore 1. And before I finish sort of completing this instruction down here towards the bottom of my program, I'll put val1.fill and whatever value that I want to put in there. The dot fill doesn't need to go at the bottom. It could go right underneath the instruction, but it's kind of common to put all of your data down at the bottom. Otherwise, it gets difficult to read the program if it's interrupted a bunch by, dot fills and dot block words and dot strings and things like that. If the operand is a literal value, I'm going to make sure I use a prefix and put the correct literal value. And if I'm branching somewhere, then I can use another label. By the time I get here, I might not have had this label to start with, but when I know that I'm going to branch back up to this instruction here, that's when I can go back and just add a label to this instruction and to the branch target. Next, I want to make sure that I add some explanatory comments. I left a bunch off of this example program because I was running out of room. Give yourself some comments so that 2 weeks from now, when you come back to look at this program, you remember why it's working and why certain values are in which registers. And then lastly, you're going to put .end at the bottom of your program to tell the assembler that it's reached the end of the program. Okay, so to summarize, we looked at assembly language today. We identified that it's much easier and better to convert our flowcharts into assembly than straight into machine code. And we just need to leverage a program called the assembler in order to make the final conversion from our assembly language into the machine code that the computer needs. Assembly supports instructions and assembler directives, the instructions of which map directly to the instructions in the LC3 ISA, and our directives give us some ability to tell the assembler how to do its work, where to put stuff in memory, and how to make where the start and end of our programs are. And to convert a flowchart to assembly, we just have to follow these steps here. Starting from the top, we need to make sure we have our dot origin. We're going to enter the opcodes for each instruction and our operands as we need them. And then we're going to put dot end at the bottom. Okay. All right, today's quote is brought to you by Henry Ford. He said, "He who says he can and he who says he can't are both usually right." We'll see you next time.